recording's rolling. It is Friday, September 19th. You guys have your laptops up. I'm going to have you guys download a Paul Hewitt file. Here, I'll show you guys first. Some of you guys may have done this already. And also unzip it. It's from a zip folder. So while I'm doing that, I'm going to play a Paul Hewitt demo in the background involving a bed of nails, which, by the way, is going to connect to this Pythagoras cut. You guys remember this cut? Okay, so the premise went, I filled it halfway with water, the water stayed in the cup. I filled it to the brim and the entire cup drained. So we're going to debrief that and wonder how many guys figured that out. I'm about to get volunteers here in a minute. So then after that, my goal is I want to solve tension with three strings with you guys, which is this right here. So if I give you the angles and the weight, can you solve for these two tensions? We're going to do that in class. Then we'll solve a car braking to a stop, like what braking distance does it need? I'll give you the coefficient of friction. And so, oh, look, I updated this one. Got a negative there. I can go that. And then we'll have enough time to at least set up this incline, and that's as far as I got in my earlier class, and then the bell was ringing. Right? Okay, so that's the goal. Guys, this weekend, homework this weekend. You guys know this is a college level class, right? College level class. And in college, you guys know you only go to class 3 days a week usually for one semester. Right? So a lot of it's up to you to learn. So I'm giving you guys some options here. You guys got your planners, so choose what you want to do. You guys know the more of these you do, the better you're prepared to be in this class and for next week. So do at least one or two of these things. So I'm about to have you guys download some Paul Hewitt files. You could have a Paul Hewitt watch party. Oh yeah, Paul Hewitt watch party. You could read chapters from the book. I've scanned and uploaded those chapters, or my honors class has the textbook online anyway. You could set aside 30 minutes to enjoy reading and thinking about the printed puzzles. I did put these puzzles in your hand, so you can read these, start thinking about. You might be able to solve some of them, probably not all of them, right? Right? What else could you do? You could read the AP classroom questions for AP. By the way, I don't have due dates for either of these yet, but probably a couple of weeks or so. Right? Explore the adventure that you recorded this week in your notes. I review your notes. Right? I bet you guys have a bunch of free body diagrams, a bunch of scenarios. We'll do some today. Quiz corrections. You guys picked up your quizzes. So on a separate page of paper, you can write out how to get the solution to any one that you missed. If you staple that to your quiz and turn it back into me, then I'll give you partial credit back. You could rewatch your favorite Google Classroom video that I'm recording one right now. Right, so here we go. You guys got your laptops up. Guys, go to Google Classroom. Right? And here's zoom in a bit here. Google Classroom. Right. So we're on today's date 29. So I'll upload this video later. But if I scroll way back to go back to week 1. So week 1 in this class, and then go down to, let's see, I have to view more, I think. Keep going. There's Paul Hewitt demos. You guys see Paul Hewitt demos? Hey guys, there's 2 zip folders. So I can right click on one, open in a new tab, and then click download. Now earlier today they were telling me that this was too many gigabytes. It wouldn't actually download on a school laptop. If you run into that issue, I guess you could download it at home. But here, see if you try your luck here. Right? So if you download it, you'll have it ready to go. And then you do have to unzip it. It is a zip folder. Okay, you guys know how to unzip it.
Is it the free money guy?
Right click, extract. Well, download as much as you want. So free body diagrams, I think I uploaded yesterday. That PowerPoint, yesterday's PowerPoint is also uploaded. Guys, this was way back to the very first week of school. In fact, I uploaded this before I ever saw your faces. August 2nd. You guys remember that? Back when you guys were playing on the beach, whatever you're doing in the summer? Yeah. So download these either today, right now, or at home if it doesn't work. Right? And then, you could have a Paul Hewitt watch party. In the meantime, here, walk around and help you guys out. Help you extract a zip folder and whatnot while I'm playing this.
Let's show, by the way, it's Apple. And these as well. These are sharp nails, gang. Okay? About an inch apart. If you don't know what an inch is, think about 2.54 centimeters. About 2.54 centimeters apart, all right? And Paul is going to... You sure these are Teflon coated? No, these are the real thing, honey. This good. You know what we don't do it the other way around? That's a good question. This really is dangerous. And Paul's a little more foolish than I is. No. Paul's got more area. I think you know. Okay. On your back, Robinson. Oh, days where Yeah. It's for science. Have to have Red Sox. You guys protect yourself. Protect yourself. Yeah. Okay. Okay. Here we go, gang. Here we go. Hey, 1, 2. I should tell you. I should tell you, this is not mind over matter. It's not what kind of granola or bean sprout or meditation that Paul does. You know what this is all about, gang? Physics. Yeah. Okay, let's see it. Here we go. 1, 2, 3.
Okay, so get back here. All right, so I've been walking around, helping you guys out. Some of you guys, I think, actually were able to download it. Some of you guys, it was saying network issues. So I think it's like internet bandwidth here. And some of you guys didn't have space on your computer, but maybe you did a home computer. Right. So some of you guys it worked, some not. But yeah, I do highly recommend, because I'd like to show you more of those. But what you guys just saw is bed and nails. This was an idea having to do with pressure. So this is, you guys remember pressure is force per unit area. So like if you lie on a bed of nails, you have some weight. Couldn't you quantify your weight as a force in newtons? Right. Yep. And then would you rather lie on 1 nail or 1,000 nails? 1,000. Let's go with 1,000 because your weight then would be distributed over 1,000 times the head of a nail area, which is a tiny area. But okay, but that would be less pressure, right? Like less force per nail, right? Yeah, that would be better. Right. Okay, and that has something to do with how this Pythagoras cup works. Okay, so remember, fill it halfway, the water stays in the cup. Fill it all the way to the brim, and the entire thing drains. The question is, all right, so there's a straw hole here, and here's the straw hole here. Right? How's the straw connected on the inside? Who figured it out? Who knows? Who knows how this works? Who knows how it works? What do you think?
And works based off the atmospheric pressure.
Okay, yes, you do need atmospheric pressure. Guys, it turns out you're right. This would not work in the vacuum of space. Like if this was on the moon and somehow the water stayed liquid, yeah, it wouldn't actually work. Right? Okay, so how does the straw connect? Right. Guys, how about this? If the water fills up to here and it does one thing, and then here there's a complete different state change. How many of you guys think the straw has to somehow make its way up the side here? That would only make sense, right? Right, somebody with that? Right. Right, how many of you guys are thinking this? How many of you guys are thinking about like whoa, about like that right there. Right, that right there. Right. Have you guys ever looked, say, underneath your sink or back behind the toilet and seeing do something like this? Right. It's like the siphoning effect. So, I have a poster for it too. That's gonna download that from the book. So if you fill it halfway, here's what it looks like, cross section. Fill it halfway with water. Some water goes into the straw, but only up to that level, and then it's just equilibrium, so it stays stable. Right? But if you fill it to the brim, now it floods the straw. Right. So water starts leaking out. Right, then it starts draining, comes back to the level it was before. Right, same level it was before. But now this one's different on the right because look at that. Now the straw's flooded. You guys see that? And all the rest of the water gets siphoned out until it all gets vacuumed out. All gets siphoned out. Yeah, you guys see that? Right. And why would this not work in a vacuum? Because guys, if this was a vacuum, and again somehow it stays liquid. That is fine. If this was a vacuum, then when it gets down to about here, wouldn't this liquid just split? And then the whole process would just stop right there, right? And then, okay, you get a little more drainage, but otherwise this just stays right here, right? But the fact this is under huge pressure, this is not able to split, at least not for this height change, okay? Right, is it? Yeah, so this does need to be, you guys remember how much pressure we're in? 14.7 pounds per square inch in American units. So it's like a 14.7 bowling ball on every square inch of your skin right now. Yeah, that's what you're sitting in right now, compared to vacuum space, right? Or 101,000 Newton per square meter, 101,000 pascals. That's in the metric system that we use in this class. Right? How about this? That's also equivalent to if you dove down in the pool. Right? You guys ever gone diving down the pool in the deep end, all the way down to the bottom of the pool? You can feel that pressure increasing. How far down would you have to dive before you felt the pressure effectively doubled to 2 atmospheres? Because we're sitting in 1 atmosphere now. You dive deeper, the pressure only goes up from there. How deep would you have to go?
2,000 meters.
How many meters?
2 meters.
It's about 10.3 meters, which by the way is about the width of this room. So if you take the width of this room, turn it sideways, fill it with water, go all the way to the bottom. You go from 1 atmosphere here down to 2 atmospheres here. Okay, which also, by the way, tells you how far you can pump up water. See, people figured this out a few hundred years ago. There's, could you guys imagine this could be a big old lake right here? You guys see this big old lake? There'd be a town on top of the hill. They start pumping up water, and say, "Oh, hey, that's a good idea." So then all the towns started pumping up water from the lake below. Right. But they realized after a while they could only pump up so far before sort of the pressure would run out. Guys, how high can you pump before the pressure runs out and you can't pump up anymore? Yeah, about 10.3 meters, about 30 something feet. That's right. It's the same thing. Right? What's the longest straw you can use on Earth and it still works? About 10.3 meters. Yeah, anything beyond 10.3 meters won't work. What's the tallest Pythagoras step I could make and it would still like siphon the water? 10.3 meters. Aha. All right, you guys got it? All right, something? All right, so there's a little pressure right there. All right, let's do this one. You guys got your notes out? We're going to solve one of these. So this would be asymmetrical joint and tension. This is going to be an equilibrium puzzle. Equilibrium. We need some equilibrium right here. You guys got some paper out. Got some paper out. Did you solve this? So about the middle of the paper, I'm going to look mid-left, put a big old dot to represent the center mass dot. That's going to represent this point right here, where they all come together. They all come together right here. Okay. You guys got rulers nearby. So let's have one force going straight down, and that's going to represent a weight. I'll label that either F sub G or M times G, right, to represent the weight. Is that true? Okay. Here, I'll give you guys a number. Let's call that, change it to PT for a number. How about an even 100 newtons? It's exactly 100 newtons. Okay, just making something up. Right. And then let's have a couple of string tensions. Could have some string tensions holding this up. Let's have one going, let's say kind of up and to the right, but more right than up, so kind of horizontal-ish. Okay. And let's have one going up and to the left, but more like vertical. So maybe more like this right here. I think it's pretty good. Okay. Guys, copy as closely as you can what I've drawn. Right, there's a reason I've drawn it this way with those relative magnitudes, and you'll see as we start solving this, it'll emerge why I drew those like that. Right? I'll call this tension on the left side, and I'll call this tension on the right side. Okay, so tension left, tension right. Okay. Now, what those tensions are, do you think it has something to do with how much weight, like 100 Newton weight? Do you think it also has something to do with exactly what the angles are? Like if I change the angles, do you think the tensions change? They do. So I do have to give you some angles. So we're going to add to this picture. I need to introduce a Cartesian system. Now the system I'm going to introduce, and I'll have one axis that runs parallel to gravity, so straight down vertical, which my weight vector obviously is already aligned to. So that's good. I don't have to break that into components or anything. But what about these tensions? Right? It looks like they're off on diagonals. So let me get a horizontal axis. So it's running perpendicular to that vertical axis. Right, so got like an x-axis and a y-axis. And I'm going to break these tension vectors into components. So how much to the right, how much up, how much to the left, how much up, and then be able to make sense from there. I do need to give you the angles. So let's call this angle alpha. Let's say 30 degrees. Like 30 degrees is a pretty good one to be familiar with. So let's run that. And I'll make this angle over here. Let's call it beta. And let's go wacky bananas with this. How about 51 degrees? Okay, so just something crazy. All right, we'll see what happens. I don't know. I haven't worked this out ahead of time. Okay, so let's break this into components. So this one up and to the right is pulling up kind of to the right and kind of up. Bing! Just like this one on the left side is pulling up kind of to the left and also kind of up. Bing, bing. Something like that. Okay. You see, I effectively replaced those tension components in terms of these, or those tension vectors in terms of their components that I just drew in pinky. Notice I also dashed them. Right? Guys, AP is really strict about that. If you make your component solid, then they don't even give you credit because it's sort of like you're double counting.
Triangle on TR. What is it?
TR? This is alpha is 30 degrees. Yeah, so this angle alpha is 30 degrees. This angle beta over here on the left side is 51 degrees. Now that's relative to the horizontal. Guys, could I have given you the angles from the vertical instead?
Yes.
Yeah, so look, you might do something like that one day, right, but today it's like that. Right, which, okay. All right, so here's your conditions for equilibrium. Equilibrium. Right, so right now we're just looking at forces. Right, so I have the sum of the forces in the y direction has to go to 0 newtons, and also the sum of the forces in the x direction has to go to 0 newtons. Okay, okay, that's my equilibrium conditions right there. I'm going to use those conditions to set up a system of equations. Right, guys, that. And what does that mean in terms of the picture? Well, the sum of the forces in the y goes to 0. Does that mean that this left one pulling up plus this right one pulling up, like just the upward components, that plus that up? And then if I subtract the weight down, that sums to what? Zero. Up plus up minus down goes to 0, doesn't it? That's what that one says. And what does this other one say? Does it say this one pulling to the right and this one pulling to the left? Do those also zero out? Right. See, I was trying to set up my picture that way, and it worked out. Guess this one pulls right as much as this one pulls left. Get that? Right. If you have a really good picture, then that's also the case. Okay. So I know that guys, which tension is going to be bigger? The one that's pulling more vertically-ish, the one that's pulling more horizontally-ish. Which one's? Yeah, guys, this one's always the bigger tension, and you can see it. It stands out right here, doesn't it? Okay. So let's set up the system right here. So take this one, this condition. I'm gonna go. Oh, whoops! I didn't write this yet. So let's fill in these. So over here, can I call this tension left times what? Sine or cosine of 51 degrees? Sine, because it's opposite. So sine 51 degrees. Right here. Can I do that for all 4 of these components? Right, you guys can follow along with me. I bet you guys can figure out the other 3. This is tension left times cosine of 51 degrees. This one right here would be tension right times cosine of 30 degrees. Ooh. And then this little component right here is tension right times sine of 30 degrees. Okay. Right, so you guys got all 4 components labeled. Okay. Now, sine and cosine, can I punch those into the calculator and get exact decimals for any of it? Right. So let's do that. So what is sine of 51 degrees? I don't know that one. So sine of 51 degrees looks like 0.777714 something. Right. So over here, I'm going to put that in front as a coefficient. I'll call this equals 0.7771 tension left. Okay. We'll put it right there. Okay. And then this one down here, what is cosine of 51 degrees? Is 0.6293 something. So this is 0.6293 times tension left. Okay. Okay, so I got those in terms of decimals. I'm keeping a lot of decimal spaces. I'm going down to the nearest, what is that, 10,000th place or something. What is cosine of 30 degrees? Which is a good one to know. I see this decimal all over the place. This is 0.8660 times tension right. Right? Okay. And then finally, this little vertical component right here. Now, because this one I think you should know. What is sine of 30 degrees? 0.5, winner. Oh yeah, oh yeah. So I can call it 0.5000 times tension on the right side. Okay. Okay, here, I'll go ahead and circle all these components. So boom, boom, just make them really stand out. Boom. I'm about to feed these into a couple of equations and solve a system of equations. Here, while I'm at it, I'll circle this 100 Newton weight also. Okay, I know that. Right. Okay. Now, I still don't know what the tensions are, but I do know some kind of relationship I'm setting up. Right, guys, okay. So, all right, so now back to where I was kind of jumping the gun before. The sum of the forces vertical goes to 0. So, can you guys set up this vertical equation? Can you say a step ahead of me? Here, see if you can say a step ahead of me. I'm going to say 0.777 tension left plus 0.5 tension right minus 100 newtons goes to 0. Okay? Isn't that in the vertical? Right? How about in the horizontal? Can I set up this way? So horizontal, can I say 0.8660 tension right minus 0.6293 tension left? That also zeroes out 0 newtons. Okay. Isn't that my system right here? Here's my system. Boom, boom. Okay. All right, you guys good? All right. All I did is I said there's 3 vertical either components or forces, 3 of those. Okay. There's 2 horizontal that are in opposite directions so that they subtract from each other. Okay. And each of those conditions has to zero out along its respective axis. Is that okay? All right. Because if you can figure that out, then the rest is just algebra. Can you guys solve with either substitution or elimination? Okay. You guys do see, if you have two independent equations and two unknowns, it is solvable, right? Two equations, two unknowns. Right. What do you guys feel like doing? Substitution or elimination? Substitution, sure. Let's do it. So I'm here in a call for substitution. Substitution. So that's exactly what we'll do. So if I do that here, I'm gonna open up a new paper right here. I'll start with this horizontal type equation. I'm going to get one tension in terms of the other tension, and I'll substitute that later on into the first equation. Okay. So 0.8660 tension right. Guys, is it okay if I just, can I just take this tension left and slide it over to the other side? So we'll say equals 0.6293 tension left. That's okay, right? I just added that over. And then, guys, how do we get one tension in terms of the other? I have to divide both sides by what? How about one of these coefficients? Right? So say I divide both sides by 0.866. 0.866. Right, you guys said. So I'm isolating one of the tension. So I know the tension on the right side equals, and if I divide this out, what's 6293 over 8660? Right. Equals 0.7267 tension left. Right. Now that's an important middle step right there. You guys see out there? Okay. Good. So guys, do I know either of the tensions exactly yet? No. What I do know is this. What I just figured out is that the right tension is 72% of the left tension. Okay? Right? So now I have a relationship between the two tensions. Okay. Now I'm going to take this and substitute it back into that vertical type equation. You guys remember this vertical one that pulled in the 100 newtons? Okay. So let's set that big. So I have, here, I'll write it out right here. 0.777 tension left plus 0.5 tension right minus 100 newtons equals 0 newtons. Okay. Wasn't that, I just copy pasted that right there? Okay. Sure. All right. You guys good so far? Okay, trying to keep a pretty good pace, but might go back and recap later. Now, guys, can I just substitute right there? Substitute. Okay. And I'm about to set up an equation with only one variable in it. Thanks. So 0.7771 TL plus 0.5 times 0.7267. Also TL. Woo! Woo! Okay. Can I do this? Can I say equals 100 newtons? Just add that over while I'm at it. Is that okay? Okay. Now I can add all this together. Add it up. Add it up. Some 1 plus 0.5 times 0.7267. This looks like 1.14 tension left is equal to 100 newtons. Okay. Right. Okay. Let's get step by step. I mean, we're just doing algebra at this point. Okay. And then last step to solve for tension, I have to divide by this coefficient. 1.14. 1.14. Right. Something. Right. So tension left is what's 100 divided by that? Right. 87 point. Well, how about this? I'll round it to that. Okay. That many newtons. Okay. There's my left tension right there. There's my left tension. Right. Hey! Can I take this out and right there? Plug it in right there. And then get my tension on the right side. Right? Just substitute back there. Right. So if I take that and I multiply it by 72%, so times 0.7267, I'm getting the tension on the right side is 63.7 newtons. Aha! So now I have both tensions. 87 newtons, 63 newtons. Okay. Right. Does that make sense in terms of the picture? Let's go back to the picture and make sure. Because it looks like the left tension is more than the right tension, right? Does that match the picture? Oh yeah, you guys said it should. You guys remember you said the left one should be, I did draw this arrow vector as longer than this right arrow vector, didn't I? Yeah. Right. So here's a recap of everything we just did. Right. Okay. You have three forces acting at different angles. So introduce a Cartesian system, and then break these vectors into components so that all the components align with your Cartesian system. Okay? And then your condition is that those forces have to sum to zero along each axis, in general and also along each axis. So you can take advantage of that to set up a system of equations. So the left and the right cancel, that's right here. And this up plus up minus this down also cancel, that's this one right here. They all sum to zero. Okay? Then, next step was we took one of those expressions and solved for one tension in terms of the other, substitute that back into the other equation, and then you can get exactly one tension, and then you can do one more substitution and get the other tension. Okay? And then make sure it all checks out. Okay? You guys good?
No.
Hey, do you guys remember yesterday a question about a stubborn donkey? Stubborn donkey? What if I change this? What if I change the story? What if I put a little donkey here? Got a little donkey tail, donkey whiskers, and could there be two guys pulling with ropes at some tension, and donkey's pulling straight back with some friction force? And that would that be the exact same math? The exact same math? It's the same thing. It's the same thing. All right, you guys ready to have a car break into a stop? All right, you guys ready for a car breaking to a stop? All right, here we go. It's car breaks to a stop time. Time to break a car. Yeah, thank you. Yeah. Okay, so car time. Okay, so how much road for car to brake to a stop? Okay, of course, I'll give you guys some numbers, and let's just have a flat horizontal road, so nothing crazy going on. Okay, so here's a flat horizontal road. Here's a car, a little turtle car. I'll give this an initial velocity. Here, I'll make up a number. Let's call it about 25 meters per second. Okay, it's like highway speed. It's like I think it's over 50 miles an hour. I think I should know that. So given. Okay, so give you guys a bunch of values here. I'll give you the mass of the car as let's say 1,000 kilograms. I'll give you Earth gravity is 10 meters per second squared. Right. Okay, there is something else I have to tell you guys. Guys, what else do you have to know to be able to solve this question? Of course, I gave you initial velocity, 25 meters per second. Okay. Well, what else do I? Coefficient of friction. Yeah, guys, isn't it true? If the road is iced over, the car like skids a long distance. If you have a wet road, it's kind of medium, and if it's a dry road, real short. Okay. So here, I'm going to give you guys a coefficient of friction. Let's call it. How about 0.8? Now, this might be static friction, and maybe the car has anti-lock braking, or maybe it's kinetic friction, and the wheels lock and it skids, or one or another. I don't know. But we'll just use that as a general value. Okay. So the car brakes as soon as you could possibly brake. How much road do you need? So as the deer steps up in front of the car, right? Is everything gonna be all right? We're gonna find out. Right. So, you guys remember free body diagrams? Let's make a free body diagram on this car right here. Guys, what's one force on this car? Yeah, it's weight. So gravitational force. Pull straight down. So that could be mg. Oh wait, actually we have m. We have g. So can I just multiply those together? What is that? 10,000 newtons. 10,000 newtons. Right. Wait, that's a force straight down. What force is holding the car straight up? Normal force. Ooh, and guys, what is the numerical value of this normal force? 10,000 newtons. Yeah. So car being pulled down, car being held up. Let's cancel out. Okay. If the car's braking to a stop, what other force on the car? Friction. Because right now, as I'm showing it, the car's just going constant velocity. But yeah, to brake, I need friction force. And which way does friction force point? Back. To the left. Here, backwards to the left. Okay. Oh, guys, if you draw this exactly to scale, how long should I make this? Like if my diagram is exactly to scale. And the answer is right here. You guys see this mu of 0.8? Okay. That tells guys what mu is. Mu is the ratio of friction force compared to normal force. Okay? Right? Isn't that true? Okay. Or you can write it this way. Friction force turns out is mu times normal force, especially if it's like kinetic or maximum static, whatever we think of it. Okay? Okay. So this 0.8, could you interpret this as 80%? 80%? So whatever length this normal force is, shouldn't this friction force be 80% of that length? Right? Like on the paper? And I'll label that friction force right here. Okay? All right, you guys good? Okay. Let's go ahead and solve that. friction force, I know is equal to coefficient of friction times normal force. That's what I just wrote right here. Right? So I'm saying 80%, so 0.80, times the normal force of 10,000 newtons. So 10,000 newtons. Okay. And does that come out to what? 8,000 newtons. Right. So this friction force right here is 8,000 newtons. Right. You guys got that? Right. Because it's 80% of 10,000, which is the normal force. And the normal force is equivalent to the weight. Okay. Right. True. You guys see how it's all click in place? All click in place. Okay. Okay. So now that you know the forces on this car and you know its mass, let's see. I know the forces. I know the mass. That means I can solve for the. If you know force and you know mass, acceleration. Aha, acceleration. So that's called Newton's second law of motion. Okay. The acceleration is the net force divided by the mass. Okay. Now, when I say net force, okay, I see three forces. But guys, what is the net force in this case? It'd be how much? Do the two verticals cancel? Two verticals cancel? I mean, the car's not moving up or down. So what's left? 8,000 newtons. You guys see 8,000 newtons? Is it okay if I make that negative? Is that okay?
Yeah.
Because the car's moving to the right. Its force is pulling to the left. Right. And how much is the mass of the car? 1,000 kilograms. 1,000 kg. That came from right there. Okay. Is that okay so far? Right. So there's a bunch of forces on the car. A couple of them cancel. That leaves you with one remaining force. It's the one I circled, which is the friction force, which is the net force. It's 8,000 to the left. Okay. Okay. So if you divide that out, the acceleration of the car is what? -8. Yeah. Newtons per kilogram. That's also called what? Meters per second squared. This is the acceleration. Guys, look for that in the future. It's really common, especially with gravity fields, to describe gravity fields in Newton per kilogram. It's the same thing as meters per second squared. Okay? Okay. Okay.
There's A equals F, and what is that?
F sub net. Net force. Right. Okay, so guys, Newton's second law of motion is the resulting acceleration is the net force divided by the mass. Okay? So net force over mass. Net force in this case is the friction force. So 8,000 newtons to the left. It's acting on a mass of 1,000 kilograms. So this is the rate the car's slowing down. Okay? All right, you guys good? All right. Okay, so we're in a really good place here. Okay. But what's the question? How much road? Like, could that be a distance? Could that be a distance? Huh. What's that going to be a job for?
Kinematic motion.
Kinematic motion. Isn't that this right here? Is that this right here? All right. I have a bridge poster. Here's my bridge poster. So here's the force for the trees view of what we just did, what we're in the middle of right now. So you guys found net force divided by mass to solve for acceleration. So we're like crossing this bridge. Right? And guys, if you're solving for a braking distance based on speeds, and nobody brought a stopwatch to this party, then is that first, second, or third equation? Third. That's the third one. Oh yeah. I got a class full of winners here. Third one. So let's go. Final velocity squared equals initial velocity squared plus 2ax. Now, brake to a stop. What's final velocity?
0.
0. So 0 squared, whatever, still 0, equals, I gave you the car was going 25 meters per second initially. Right, that's being squared plus 2 times, for acceleration, I'm going to say negative 8.0 meters per second squared, and then times the braking distance. Okay. Oh yeah, one equation, one unknown. You can solve for that, right? 25 squared, subtracted over 625, I think. Okay. All right, let's see what we're getting here. There's 625 on 16. I'm getting a braking distance of 39 meters. 39 meters. All right. You guys getting the same thing? I think that sounds about reasonable. Guys, is that about a third of a football field? Oh, yeah. So see, if you were driving at highway speed, so you're driving out on US 1, and you slam the brakes and brake at a pretty good rate with dry road and tires, new tires. Yeah, take you to that part.
Is there a
Yeah, correct. Yeah, so if there was a deer that stepped out in front of you and it was like 50 meters in front of you, yeah, the deer's okay and you're okay. All right. Let's do how are we doing here on time? We got okay, we got just enough time, just enough time. Perfect. We're exactly where I was my last class. Do you guys see this one here? Great. Here's what we're doing to finish class out today. I'm gonna build your guys' motor skills. We're just gonna construct this. All right, you guys ready to construct this?
Yeah.
We'll construct this, and then whatever question you get, well, there could be some follow up, but that'll have to be a different day. Okay. So do a block. Call this in your notes. Block at rest on incline. Okay. Block at rest on incline. Okay. So draw an incline. Okay. Right, and we'll do the full analysis for the setup here. Okay, and then draw a block. Okay. Now this angle I'll call theta, and I'll just leave this in terms of variables today. So that theta could be kind of anything, right? Could be 30 degrees, could be 40 degrees, could be 10 degrees. Oh, could be your car and incline lab of maybe 5 degrees or something. Draw a center mass dot on your block. Okay, got your block there? Maybe it's a little lab weight or something. Okay. Guys, what's one force acting on this block? Yeah, let's start with weight, because if it was weightless, then there would be nothing else, would there? It would just be floating around. So yeah, let's have a weight. Now have the weight going. Does the weight pull straight down to the center of the earth? Absolutely, it sure does. So I can label that M times G, mass times gravity field. I can label that F sub G. I can do that too, right? Okay. Now moving on, I'm going to introduce a new Cartesian system. Because that Cartesian system is going to be aligned to the what? To the surface. You see that x-axis is now parallel to the surface of that tilted incline, and then there's a perpendicular axis, sort of my y-axis. Could run this way, right? Okay. I'm going to make sense of the rest of this puzzle in terms of that Cartesian grid. Right? You guys have that? Okay. Let's break this weight down into components. Let's align it with that Cartesian system. So doesn't the weight do two things to the block? It sort of pushes the block kind of into the incline, and it also makes it sort of want to slide down to the left, doesn't it? Doesn't it? Okay. Guys, make sure you got this right. Where's your right angle? Is the right angle down here, or is it over here on the right side? Here's your right angle right here. Oops, I forgot to put a little arrowhead there. Notice I dashed those components. And speaking of angles, because if this angle right here, theta, is 29 degrees, is this angle up here also 29 degrees? Yes, it is. Exactly the same thing. You may sort of play an animation in your mind. Those angles always match. Right? I don't have time to prove that today, but it's it, right? All right. So could this be mg times what? Sine or cosine? Cosine. And then this little component right here is this mg times sine of theta. Okay. Guys, get used to that. You'll see that all over the place here. But I need some more forces. What force is sort of holding the block up-ish? Well, I'm looking for normal force next. Okay, guys, did you draw the normal force acting straight up against gravity? No, you didn't do that. Did you draw perpendicular to the surface? That's what normal means, perpendicular. And in terms of magnitude, this is the same magnitude as what? Mg cosine theta. Guys, it's the same thing as mg cosine theta. Right. But to be at rest, I need equilibrium. So I do still need what other force again, you guys said? Friction. Which way does the friction force point? Up and to the right, parallel to the surface. I'll call it F sub FR, friction force. Right. You guys, that's equal in magnitude to what? Mg times sine of theta. Right? Guys, could you also make a connection to friction force as coefficient of friction times normal force? Right. So if you were solving for what's the minimum necessary static coefficient of static friction, you can make a tie-in that way. Right? Yeah, that'll eventually turn into a lab. Okay, all right, so you guys good? Yeah, so perfect time in. Right, so here's here's your adventure options over the weekend, and I hope you guys have a good one. Yeah.